Okay, thanks a lot for the invitation. It's my pleasure here. And also spend a very nice week during my stay here. So today I'm talking about the recent work joined with Martin Bridgeman, Ken Bromberg, and Franco Vargas-Pallete about holography of the Loewner energy. So this we haven't put on archive yet, but I just put a draft on my webpage. That was the top, the first paper one. The title doesn't look exactly like the same this one, but it's the same paper. So what is Loewner energy? Let me just first apologize that the talk is actually not the talk about probability theory, but however, this object, Loewner energy, they arises from the studies of the Schramm-Loewner evolutions. So they're just a motivation from probability theory. But however, the results will be purely deterministic. But the hope is that maybe this work would be able to open to new research directions about how we can lift the two-dimensional random conformal geometry into three-dimensional series. Okay, what is Loewner energy? So for a Jordan curve, so I will only be considering Jordan curves, the closed simple curve sitting on the Riemann sphere. The Loewner energy is the energy that is a quantity which measures the roundness of the curve. So it will be always larger or equal to 0. And one definition, maybe the simplest definition of this, is that if you take, the unit disk, and I take a conformal map, I will call this bounded domain cut out by gamma called omega, and the complement omega star. I take a conformal map F from the unit disk to omega, no matter which one. And I take another conformal map H, which I would have to ask it to fix infinity. But this is the only requirement. I take these two conformal maps. The Loewner energy of gamma is defined as 1 over pi integral over unit disk prime over f prime squared multiplied by the Euclidean area metric plus 1 over pi, the same thing for H. So for this term to be finite, I really need to set H infinity to infinity. And the last thing is 4 times log of f prime of 0 divided by h prime of infinity. Okay, this is definition. So one can first check that if gamma is a circle, just a round circle, the same as this one, I can take f and h both to be identity map. This functional is Loewner energy of gamma equals 0. We also have to justify a bit, like I said here, I don't need to take any f, so we have to justify if I change another f, this functional doesn't change. It only depends on gamma. But actually more is that this quantity is actually PSL2C invariant. In which sense that, so element in PSL2C, I will view this as a Möbius transformation on the Riemann sphere. So this is a map from Riemann sphere to the Riemann sphere. If I call it A, then the Loewner energy of gamma is equal to the Loewner energy of the image. It's not exactly clear to see directly from this computation, but actually from this definition, we can derive another identity of the Loewner energy in terms of determinants of Laplacian. So alternatively, the Loewner energy is equal to 12 times log determinant of the Laplacian on the sphere. Whenever I talk about Laplacian, I mean this is a Laplace Beltrami operator, which would have depends on a metric. And here I can take the metric to be just the round metric. This is this choice actually wouldn't matter too much. I'll comment on that slide later. And here, the determinant of Laplacian, we need to regularize it, and the particular regularization we take is the zeta regularization. And because this operator has a kernel, usually the zeta regularization is not the best guide to consider. We always would take out the area of S2 with respect to this metric. Okay, this term doesn't depend on the curve yet. But then I would take out log determinant of Laplacian of omega G S2, and the symmetric term, determinant of zeta Laplacian omega star G S2, plus universal constant. And this universal constant is basically to make the Loewner energy of this round circle being 0. And here I also have to say this is the Laplacian with Dirichlet boundary condition. So this, how we can get from this identity, this definition to this one, essentially this comes from the Polyakov-Alvarez formula. You can compare the metric in two different the determinant in two different metrics with conformal change. One important fact is that this quantity here, these 4 terms altogether, is a Weil invariant. In the sense that if I multiply this round metric by some smooth function exponential phi, each of those terms will contribute some Weil anomaly, and they will cancel out. And therefore, from this definition, you would see that if I apply my gamma by a fractal linear transformation, I can just view this as not changing the curve, but just changing the background metric by a Weil scaling. And from this this thing, you will see that this identity follows immediately.
So in the definition you gave over here with the F's and H's, is this true for any F and H? I mean, it's independent of F and H.
Yeah. So this, if I curve my curve, so the right hand side only depends on the curve, no matter which F you take. Yeah. And H, I just need to ask it to fix permanently.
Okay.
Yeah. All right. So first of all, this quantity is definitely not always finite. Here we are kind of asking some integrability about conformal maps. If my curve is smooth, by some Kähler theorem in complex analysis, it will say that this conformal map extends continuously or smoothly up to the boundary. Then every term here, they will be finite. But a priori, not all curves will be finite, has finite energy. So the definition, so gamma is a Weil-Petersson quality circle. If this integral f prime over f prime, this term is minus. And one can, then this is definition, but then one can show that if this is finite, then it will also imply that the integral of h prime star will be finite. It can be also equivalent to the Loewner energy of gamma is finite. There are actually other characterizations. I can continue this list. There are like more than 20 lines. But another one we will be using is that you can also look at the integral of the Schwarzian. So let me just recall that Schwarzian of f, this is that involves the third derivative of f minus 3/2 prime. Schwarzian squared multiplied by 1 minus c squared. So this is the inverse of the hyperbolic metric. The Schwarzian should be viewed as a quadratic differential. So here you have a 2-2 form. I divide by metric, I get 1-1 form. So this quantity is the right quantity to consider. And this is finite. This is also equivalent. So this is definition of all these theorems. I think this I should probably give it to Cui, Taylor, they're quite independent. A lot of people have been working on that. And there's a lot of other characterization of the Peterson quality circle. Another one is that there's something called Wronski operator. So it's an infinite operator associated to each Jordan curve. This is, we call it G. The definition is not very important here, but this condition will be equivalent to that G is Hilbert-Schmidt. And when it's Hilbert-Schmidt, we can define a determinant, log determinant of identity minus G star G. When it's Hilbert-Schmidt, the adjoint of G times G will be a trace class. You can take identity minus the trace class operator. Its determinant is taking the product of all their eigenvalues. So being trace class will tell you this term is well defined. And not only this term is well defined, but if you multiply this by minus 12, this is actually equal exactly to the Loewner energy. So this is another place where you see the Loewner energy appears. So for us, for probabilists, how I started to look at this Loewner energies because there's a relation to Schramm-Loewner evolutions. So from motivation. So here, this Loewner energy can be interpreted as a large deviation rate function of SLE loop, SLE kappa loop. So this is some random fractal curves which has a one parameter kappa. So this, if I ask this curve to be roughly equal to gamma, as kappa goes to 0, this probability would decay like exponential of minus Loewner energy of gamma divided by kappa. So actually, this is not the exact theorem that we have proved. We have done this in several cases, like caudal SLE. This is believed to be true for also SLE loop, but one just have to formulate. There's a lot of things to be clarified. What do you mean by being close? What do you mean by even probability of SLE loop? So this relation can be viewed via the driving function. Description. So I'm not going to enter into this discussion. For those who are interested, I just gave an 8-hour lecture at IHES about all the probability behind this Loewner energy.
But does it have implication for kappa finite as well?
Yes. Yes. So for the finite, it's a little bit different. So this is for, we can also look at what the probability of SLE kappa being close to a curve. this can be interpreted as the density of SLE loop as exponential of a central charge, which depends on kappa divided by 24 times the Loewner energy of gamma. If you let kappa goes to 0, you would exactly recover the same rate. But what do I mean by this tilde here? So this will be interpreted in terms of conformal restriction property. So the main difficulty here is that when I say that probability, the density of SLE kappa is proportional to this quantity here, is with respect to a certain Lebesgue measure, right? And we don't know what this Lebesgue measure means. But if you compare the SLE loop in two different domains, then I can take the ratio, I can talk about their Radon-Nicotin derivative. And in that way, you just assume that this Lebesgue measure will cancel out. And then this conformal restriction property then can interpret this identity. And the central charge, this is an explicit function of kappa. So this is the relation between the Loewner energy. There's another place where this Loewner energy appears in probability is that this is, we're not going to use it, but just a side remark, by a paper 2 years ago, Johansson, he proved that this Loewner energy appears in is constant term in the large n expansion of Coulomb gas on gamma. So you take a Jordan curve and you put the n particle on the curve. All the particle can only move on the curve, and put the Coulomb interaction among this n points, and then compute the partition function, letting n goes to infinity. It's blow up, but there's a natural way to cut off the n. The remaining term is related to the Loewner energy.
So where are the particles on the
curve? They're on the curve. The curve is given, and yeah. So it may be exponential. There's some factor as well. Okay.
So will these particles be distributed in the limit based on by the harmonic measure?
Yeah, it will be harmonic measure viewed from infinity. Yeah. So this is actually closely related to this identity. What Johansson did is that he computed this partition function and relate to the Gronsky operator, and he showed that this constant term can be expressed in terms of Gronsky operator. And then this identity is shown by Teichmüller and Theo. Then to Loewner energy. Definitely the relation to SLE, etc. This is another story. Okay, this is the last thing about this Loewner energy it appears quite unexpectedly in another context. So this is the work by Teichmüller and Theo again. So they actually studied, they have defined the right-hand side. They call it a universal Liouville action. They definitely don't look at the Loewner transform SLE at all. They just define this quantity on the right-hand side, and they say that this Liouville action is a Kähler potential on Weil-Petersson universal Teichmüller space. And this universal Teichmüller space, you can just view this as this is corresponds to the space of gamma Weil-Petersson quality circles. So there's a way to identify one element one Jordan curve with an element in the universal Teichmüller space, and there's a lot of geometric structure on this space. And there's actually a unique Kähler metric on this space, which is satisfying the homogeneity. And they also show that this quantity is a very important quantity on this space for being a Kähler potential. We will not really, so this is the result we're going to show today is to write this Loewner energy in terms of some quantity in the hyperbolic 3 space. And that's really motivated by this statement. As a Kähler potential, there's a lot of previous work on the other manifold where one can express the Kähler potential of the Teichmüller space as a renormalized volume. So motivated by that, we started our work here. Let me just move to the hyperbolic 3 space. So one observation is that this PSL2C Möbius transformation, they're exactly the isometry group of the hyperbolic 3 space. So with the hyperbolic 3 space, you can do this as just a half space where the metric, let's say this is Z. The metric is just the usual Euclidean metric divided by Z squared. And or you can draw it on the ball model. The 3 space is what is inside. So the metric is the usual Euclidean metric divided by 1 minus R squared. Like this. So the geodesic in this space, if you take 2 points on the boundary, if you just draw a line across here, and you look at this slice, there is just a hyperbolic 2 plane. And the geodesic in the hyperbolic 2 plane is this semicircle. The semicircle looks like this. These are the straight lines in hyperbolic 3 space. We can also talk about planes. Planes in hyperbolic 3 space, these are just they are just half sphere in the Euclidean space. If you take any 2 points, this geodesic will be lying inside this plane. So the planes in H3, well, they're in one-to-one correspondence with the circles of the conformal boundary. So now we view this C hat as the boundary where also infinity is adding to it. And now if I have a Möbius transformation, a PSL2C element, it maps circles to circles. And what it's going to do to the hyperbolic 3 space is just mapping those half sphere to half spheres. And this in fact gives you a isometry of H3. So every isometry of H3, if you look at what it does to the boundary, it turns out also to be a conformal transformation of the boundary, and which has to be a Möbius transformation as well. Okay. So we'll use these 2 models, both of them. So since our Loewner energy is PSL2C invariant, it's very natural to ask, can I express this Loewner energy in terms of some geometric quantity in H3? There are actually a few works before. By Chris Bishop. He says that gamma is a Peterson if and only if this curve bounds a minimal surface for which had this surface sigma with finite renormalized area. Minimal surface, it just means that the mean curvature at any point is 0 of this surface. The renormalized area, so if you just want to compute this area, like because this surface comes to the boundary, this area has to be infinite. The renormalized area does the following thing: you cut the surface like at the height epsilon, Euclidean height epsilon, and you take out also the boundary length of this boundary. And this limit exists if and only if gamma is Weil-Petersson. And this renormalized area is also motivated in ADS-CFT correspondence with like Takayanagi, especially they argue that this should encode some entanglement entropy using renormalized area. But there's one thing which is a little bit not so nice in our story, like is that if we want to talk about the Loewner energy, first there's no there are arguments saying that the Loewner energy of gamma is not a simple function of the renormalized area, and their difference is unbounded in some sense. And the other thing is that there's not only a unique minimal surface bounded by gamma. So already, if you want to discuss the identity between the Loewner energy and the renormalized area, you have to decide which one you want to talk about. You can just try to argue, okay, let me take the minimal one, but still it feels a bit not so natural. Okay, Chris Bishop did another thing. He says that I can also look at the convex hull of this curve. So convex hull just means like you take any 2 points and you draw this hyperbolic geodesic in between, any 2 pair. So now they're not going to form a surface. It will give you something which has some thickness. But now this convex hull is uniquely associated with the curve. And another way to draw this convex hull is that you can just draw all the circles, which is not touching the curve, and you carve out the half sphere, you cut all of them out. Like in the R3, how you draw the convex hull, you would just take all the planes which doesn't intersect the set, and you cut them out. And here you can do the same thing. You can cut out those planes. There's half spaces. You carve all of them out. What is remaining is this convex hull. And what he shows is that this is Weil-Petersson. This volume would not be infinite. It would not be finite, except if it's just a circle. But this is Weil-Petersson if and only if the integral of the thickness is finite. So sigma, I'm just taking sigma being one of the surface, one of the boundary, and then delta is the thickness. You take the distance from this point to the other surface, and he argued that it's sigma delta square integrated against the area. Here, area really means the area induced by the hyperbolic metric. This is finite. But if the volume is finite, then what you want to do is integrating the thickness without the square to the area. But here it seems that for the convex hull they are too thick. But this condition will be the L2 integrability of the thickness. Okay. So finally, our result. Just draw here. So our theorem is when gamma is smooth enough, C5 alpha, with some alpha strictly larger than 0, we have 1/4 of the Loewner energy of gamma equals exactly to some volume associated to gamma minus integral of the mean curvature on the two surface. I will define these two surface. My curve gamma. We say that there is a canonical way to associate to each Jordan curve two surface. Those are called Epstein surface. Sigma and sigma star. This domain is omega. And the volume of gamma is the volume in between these two surfaces. And this integral is the integral of the mean curvature on both surfaces. Again, this area is coming from the hyperbolic, induced by hyperbolic metric. And this is called the renormalized volume. Also W volume. Two things.
Sorry, are these two surfaces the boundaries of the inner and outer convex hull?
No, for the convex hull, the volume will be always infinite. These are much thinner. They're actually contained in the convex hull. I will define it in a second. But let me just state also for the result when gamma is Weil-Petersson, this is the optimal thing we could expect for. It's Weil-Petersson. So far, we can show that we have the inequality. And we do believe the equality also holds for Weil-Petersson.
Also, the 5 is not natural. I mean, is it natural by scaling or?
Which one?
The 5, the C5.
C5 alpha.
Oh, C5 is, it's not natural at all.
Okay.
Yeah, it's just the most difficult part is to show this term is finite. We can show that if gamma is Weil-Petersson, if and only if this term is finite. So this is always this is nice. But this one, because they're coming really close to the boundary, if the curves are smooth enough, we can show that these two surfaces, they coincide up to second order. So the difference between the thickness would be like the epsilon cube. So that if the height is epsilon, the width is epsilon cube. And this is the order for which we are able to show the volume being finite. And why we have this inequality, so the argument is that we use a family of smooth curve approximating a general curve. All we can show is that the energy in the limit, the volume in the limit is lower semi-continuous, so the volume may drop in the limit, but it cannot increase. So we just have this inequality here. Okay, and this is actually, this renormalized volume actually will be very natural. There's a deep link with the Liouville theory. For instance, this quantity will have the same conformal anomaly as the Liouville action. But I haven't to tell you how this is defined, so let me just say define it. So let me use the ball model. So Epstein map, it's going to associate for you if you have a metric on the open set, use an open set of the sphere, and a metric, say exponential 5 times the round metric. So if I give you this data, the Epstein map will give you a map from U to the hyperbolic 3 space determined by this metric. And how does it go? So let me just take a, let's say this point of theta, the sphere. And for x, inside H3. Now this green is for something which is in the ball. I'm going to define the visual metric called the mu x. How does it go? So there exists an isometry of this is x. There exists an isometry called hx, which will map my x to the center. This isometry is not unique, but the remaining degree of freedom, these are SO3. These only all the rotations fixing the center. So hx, you can view this as the isometry of the H3, or on the boundary, this will be just a Möbius transformation of the sphere. And now here I have this metric, usual round metric, and mu x is just a pullback of the round metric by this hx. So this is a metric on the sphere viewed from my point x. All right, now I define this set. So this set will depend on theta. So this is theta again, like so this is on the sphere. This will depend on phi of theta. This is collection of all the x inside H3, for which mu x at theta equals to this metric. This is, if I draw here, this is a horosphere. So it's a sphere which is tangent to the point at theta. And these are all the points from which you have the same, the visual metric gives you the same visual metric at theta. This might be easier to see why this is a horosphere is that you can, if you map to the upper half space, my theta is infinity. If I have a point which gives you this metric, and the other points will be obtained by only translations in the 3 space. These will be the same, the points of which giving you the same visual metric at infinity. I'm just saying this, why this is a horosphere. This plane, this is the horosphere rooted at, centered at infinity. If you put it back to the ball model, you will just get this sphere tangent to the point. And like for instance, if you look at what is inside the ball, the visual metric will be larger. Outside of the metric ball, it will be smaller. And we can also show that, say that if I take phi plus 2t, this would be simply, it's all, and again, another horosphere. So for t larger than 0. Then this will be this whole new horosphere will be also horosphere, but we will have the distance t, this distance. Distance t here. Okay, and this can be checked from the definition. So now the Epstein map, what this does. if I give you a family of metric, all right, so this metric is defined, say, on this part of the sphere. This is my U. At each point, I have such a horosphere. The Epstein map is going to give you a map from U to inside of the ball, and they give you some surface, which inside, such that all this horosphere has to be tangent to this surface. So if like here, I'll draw another horosphere. Like for instance, if my horosphere are all very small, like say if I take 5 plus a very large number t, all the spheres are really, really small. What the Epstein map is doing is going to, the surface will be just the envelope of the horospheres. And you can take the Epstein map will be sending this base point to the point where it touches the surface. Right, let me give you one example. I will look at this metric to the lower half sphere. I call it, hyperbolic metric. On disk. Disk is this part. If you write in the complex coordinates, well, this metric is simply 4 over 1 minus c squared. And I also recall that the spherical metric in the complex coordinate, you would have exponential 4 dz squared 1 plus. This is the round metric. This is the hyperbolic metric. And there is one point, this point, say this point is 0, corresponds to 0 in the complex coordinate. What you see is that g of d is the same as g of s. Right? This is when z is 0, they give you the same metric. Okay, so this is the case where phi is 0 at this point. Therefore, well, the center of this ball has to belong to the visual ball, the horosphere. Right. This is collection of points. This thing here is the collection point for which the visual metric at this point is giving you the right metric. And here I have phi equals 0, so this point is inside this horosphere. So here, I have this ball associated to this metric. All right. So now if I ask what is the horosphere for the hyperbolic metric rooted at this point, centered at this point? Well, this is from the definitions. The horosphere. So now let me take A in PSL 2R. So I take a map A, so which preserves this equator, but it sends theta to 0. Right? then the horosphere, theta of phi, this will be the same as h at 0, but with the push forward metric. The push forward metric by A is still the same metric. This is following the property of hyperbolic metric of the unit disk. So here, the horosphere at this point, if I but on the other, A is an element which preserves the equator. In particular, A preserves this plane. Its isometry is sending the plane to itself. So if I have my A would send the horosphere to this yellow ball and preserving this pink equator. In particular, if there are tangents, the tangency has to be preserved as well. So here you can directly see that this horosphere for the hyperbolic metric has to also be tangent to this plane. So in the end, what we obtained is that, so the Epstein map on the unit disk for the hyperbolic metric, its image is just this hyperbolic plane. And the Epstein map is sending this point to this point to this point. And it's not surprising to see the Epstein map it gives you a surface which is touching the boundary, because the hyperbolic metric here, the metric tensor is getting larger and larger, blowing up. Because if you look at this expression, this metric when z goes to 1, it blows up. Okay? So the larger the metric tensor is, the smaller this horosphere are. So they're very, very tiny near this curve. And that's why in the end, the Epstein surface we get is a surface which goes off to the boundary. So finally, what is these two Epstein surfaces are? Here we're just going to put the hyperbolic metric inside and put the hyperbolic metric outside. Each of them give you a surface, and these are the two surfaces I was talking about. One can first, let's check this identity for the trivial case. So when gamma is a circle, from our discussion below, so both the Epstein surface are the planes bounded by gamma. So in this case, that the two Epstein surfaces they just match with each other in the half sphere. And this would imply that V gamma is 0. And the mean curvature, because this is total geodesic plane, all the curvatures, principal curvatures are 0. The mean curvature is also 0. HDA is 0. So everything on the right-hand side are 0. And this is also Loewner energy. So we have the identity. Let me just, I think I might run off my time, but just just in terms of proof how we actually get this down, is that this is the first step. We check the trivial case, they're the same. Then the other thing is that we also need to justify why the volume is well defined. Because this is something which just goes up to infinity, very far out, and even how the volume is defined is not super clear. But we can show that if gamma is Weil-Petersson, then both sigma and sigma star are disjoint. Gamma not a circle. They're disjoint and immersed and embedded near gamma. So these surfaces, they actually might have self intersection. It might not be immersion. The Epstein might not be immersion, but everything goes very well near the boundary from which usually the definition of the volume make difference. So if we have this thing, we can cut this height to some height and define the volume as a limit. So this was the first thing. And the final thing to prove this identity is that we show the variation, the first variation match. For the Loewner energy, what we have is that so if I have a curve gamma, I put some mu is at infinity of omega, and I do a small perturbation, quasi-conformal perturbations of the sphere with T mu. The T is some very small real number. So I can multiply T mu, it gives you some Beltrami differential. And this will allow me to move my curve a little bit on the sphere. And of course, it also moves my curve gamma. We show that the Loewner energy of gamma t or dt at t equals 0 is exactly the real part of the Schwarzian of f times mu. In some sense, it says that the Schwarzian of f was the conformal map, sending the domain to the inside. Mu is supported inside omega. The Loewner energy, how much it changes, is just given by the real part of the integral of the Schwarzian of f times mu. So this is the stress energy tensor for the Loewner energy. And we show the same thing for the renormalized volume. This involves a much more of technicality. To move the curve a little bit, you have to track how the points move along the Epstein surfaces and writing everything on the surface and then project it into the domain. And that is based on essentially the work of Krasnov-Schlenker. I should put their name. And following a similar argument as Krasnov-Schlenker, they also do the renormalized volume for other three manifolds, but convex co-compact case. So I think the main difficulty here is that because this surface, they're non-compact, all the analysis is much more complicated. In Krasnov-Schlenker, they only deal with compact surfaces. So, yeah. somehow this a priori regularity assumption tells us give us some way to normalize, truncate things without disturbing the variation formula too much. Okay, so I will just stop here. Thanks for your attention.
Can I have a
Yeah.
question? So you have this formula thing like variation of the known energy is given by this
Yeah.
Schwarzschild, but I also remember vaguely you write something there, like some other things is also Schwarzschild. It's like
Yeah, right.
what's the relation? Can you,
Yeah. So this is one variation. This is one place Schwarzschild here, and actually this surface there. Here I describe this in terms of some envelope of homosphere, but actually the Epstein's work, he shows that this has an explicit formula. If I tell you what is phi, I'm able to write down what is this metric, how this map explicitly is. So it not only involves phi just tell you how big the balls are, but in order to know where is the tangent point, you also need to know what is the derivative of phi in a neighborhood. You have to know how the horosphere moves around the point in order to know where exactly the tangent point is. But so the formula of Epstein only involves the first derivative of phi. And there's a lot of relation between the Epstein surface with, especially when our metric is coming from a hyperbolic metric. Hyperbolic metric, they're related to derivative of conformal maps. Right. So I have a conformal map F from the unit disk to omega. So hyperbolic metric will involve the terms of the F prime. Epstein map would have to involve F double prime, such things. And then the surface, right, this is inside Epstein map. Epstein map would involve F double prime. And now if I want to compute the curvatures, I will take another derivative. So the curvature, the principal curvatures, here are two curvatures, they would involve like F third derivative. So it turns out in this very nice Epstein map coming from hyperbolic metric, these two things can be expressed in terms of Schwarzian of F. So they're equal to something like a Schwarzian of F. I might mess up with some sign, but so what is Schwarzian of F? This is Schwarzian of F multiplied by 1 minus c squared. And then you can compute what is the mean curvature. And you can tell what is dA. So dA is the volume element here. It will be related to the volume element downstairs as well. We can show that this is same as also the determinant. This is of the trace. So dA. So this is just k plus k minus. This is a priori, this 1/2 of a k plus k minus. This is mean curvature. But it's also equal to the product. It's some algebraic relation for this. And they're actually, both of them would equal to Schwarzian of F squared. And therefore, if we integrate this on the surface, I would get just the L2 integral of Schwarzian. And that's how we show that this is finite if and only if the curve is Weil-Petersson. Yeah. This is actually pretty nice. Really, everything is exact. And yeah.
So this formula is really like a holographic formula, right? You're going from 2 dimensions to some higher level. But if I ask, what kind of regularity do I need on gamma for this to be finite? That must be known, right? Or
this is unfortunately no. We believe it's Weil-Petersson. So this is finite if and only if this is the curve is Weil-Petersson. This is finite.
no, I'm not asking about the holographic formula. I understand that's a difficult question.
Yeah.
If I just ask about the definition of the linear energy, if I have a nice curve, I surely know that it's finite. Even so, what is it? What do we know about just the finiteness of?
Yeah.
I imagine I can do much more than maybe even C3, right?
Yeah. The best sufficient condition is C1.5 plus epsilon.
Okay.
This would imply Weil-Petersson.
That implies it's finite, right?
Yeah. But Weil-Petersson doesn't mean it has to be C1, for instance. There are examples of Weil-Petersson.
C1's not sufficient, but a little over, yeah.
This is not necessary. Like C1 is not necessary, but this is sufficient.
And if I take a square or something like that, then what happens?
This is infinite. So
Yeah, I imagine it's got corners.
yeah, the corners you would have f double prime over f prime behaving some 1 over z. This won't be L2.
No chance. Yeah.
I think maybe the C holder class is not the best one. So there's equivalent, say that the arc length parameterization of gamma is in H3 so
Yeah. Okay, thank you. That answers my question. Yeah.
I'm actually not completely sure about this. But the holder class is C1.5 plus epsilon.
Any other questions? Okay, if there are no questions, let's end the